Make this figure a little bigger. Okay, you see a triangle here. A corner has coordinates b and 0, y is 0, b, x is b. B coordinate is a cosine theta and a sine theta. As you can see, cosine theta here is a negative number because theta is greater than 90 degrees. So a cosine theta is the x coordinate, so that's a negative number here. So in order to find this all on x-axis, we draw a perpendicular from B to x-axis, and the length from this point to A, the square of the length actually, from this point to A will be a cosine theta minus b squared. Okay, and this distance from B to x-axis will be, of course, a sine theta. So we can easily prove now the law of cosines. This is the law of cosines for a triangle with sides small a, b, and c. C squared is equal to a squared plus b squared minus 2ab cosine theta, where cosine theta is the angle between the sides a and b, or on the corner c. So that's a generalization of the Pythagorean theorem, because when theta is 90 degrees, this term is 0, so you get c squared is equal to a squared plus b squared, where c is the hypotenuse, a is the other sides which are perpendicular. Okay, so the proof goes like this. The square of the distance between point A and B is, of course, c squared. Okay, and if you go back to the figure, between point A and B, you have the side C. C shows the length. So c squared is the square of the distance. Now, square of this distance from here, right under B to A, is right under B is a cosine theta, which is a negative number, minus we can write it as being a minus a cosine theta. It doesn't make any difference since we are taking the square. Now that's the length of the side. And a sine theta is the vertical distance from the x-axis. So this is Pythagorean theorem, basically. Now when you get the square on this side, you have a square cosine square theta, but you have here a square sine square theta. So since cosine square plus sine square is equal to 1, you have a square on this side. Now from here you have b squared too, and then another term which is the a cosine theta times b, you get it twice. So that's what you get, and which is basically the proof of the law of cosines. Law of sines, as you know, sine A over A, sine B over B, sine C over C. Here sine A is the angle at corner A, B is the angle at corner B, and C is the angle at corner C. Now, the proof is very simple. H is equal to C sine A. Let's go back to figure, where H is the distance, vertical distance from B to axis. That's H, and that's equal to actually C, A times sine C. A is the hypotenuse for this right triangle here, and C is the angle here, so it's A sine C. Now, if you look from this point, H is also equal to C sine A, because that's this triangle, as you can see. So it's C sine A. So we have this equality. Okay, H is equal to C sine A, which is equal to A sine C. So if you divide by A and C, you get this equality. Now let's draw another vertical from point C to the side C. So you have two right triangles here, which has base as CA here, and another base AC here. Okay, now H1 is equal to A times B sine theta. This distance from here to here is A times sine so A times sine B, where B is the angle here. Okay. Now also the same distance is equal to B times sine A. So you have this equality. Okay, sorry. H1 is equal to B sine A and A sine B. From this you have this equality. If you divide by AB, sine A over A, sine B over B, so both together you have the law of sines. Now one more thing that we have to prove here is that the addition and subtraction laws. The addition formulas are, if you have two angles, cosine A plus B, that's cosine A cosine B minus sine A sine B. If this is negative here, then this is positive here. If you have cosine A minus B, then you have cosine A cosine B plus sine A sine B. And there is a similar relation. You have sine of A plus B is sine A cosine B plus cosine A sine B. If you have negative here, you put negative here too also. So it's the sum and difference of angles and their trigonometric function. Now let's give the proof just one part. The other proofs are similar. So sine A plus B, we say it's H over A. Let's look at the figure. Okay, this angle here completes theta or C 180 degrees. But angle B and angle A also complete C to 180. So this angle here is equal to A plus B. This angle plus this angle. So sine of A plus B is here. If you call this vertical line from B to x-axis H, then the sine of this is H over A. So sine of A plus B is H over A. Okay, so that's what we have here. Sine of A plus B is H over A. Now let's calculate sine A times cosine B. Sine A times cosine B. Now A is sine C over C. Actually, what we have here, sine A is H over C basically. Sine A is equal to H over B if you H over C if you make the figure. That's A, so H is here. So this is the right triangle. Sine A is equal to H over C. And so that's what we get here. Now cosine B is equal to, here you have A's cancel out, you have H over C. Now cosine is equal to A squared plus C squared minus B squared divided by 2AC, the law of cosines. So here you have this. Now let's calculate sine B. Now if you go back to figure again, okay, sine B, we were talking about H1 here. That's a vertical line from C to side C. Now sine B is, let's call this H1, this vertical distance, H1 over A, because A is the hypotenuse if I draw a perpendicular line from here. So sine B is equal to H1 over A, and then, but H1 is equal to what? B times sine A. I can write H1 as B times sine A because there is a right triangle here. So B times sine A is equal to H1. So we get together sorry. So you have sine B was H1 over A, but I can write B sine A, which is sine A is H over C, so you have BH over CA here. Now cosine A is now B squared plus C squared minus A squared divided by 2BC. So B cancels out here with this B, and you have H over AC squared. But you have here, if you put this under this, you have H over AC squared too. So if you add these two, you have A squared plus C squared minus B squared, and plus B squared plus C squared minus A squared. That's A squares cancel out, B squares cancel out. So you have here 2C squared and cancels out with 2C squares here, you get H over A, which is sine A plus B. So that's the proof of the addition formula. And the other cases like A minus B or sine A minus B, A plus B can be calculated, can be proved actually using the same type of triangles and trying to figure out every sine and cosine. Let's continue. Now we talked about shifting vertically, shifting horizontally, scaling vertically, and scaling horizontally. Now you can write a general one like this. Okay, so A is either vertical stretch or compression, depending on less than 1 or greater than 1. And B is for horizontal stretching and compression. B is vertical shift, it could be positive or negative, and C is the horizontal shift. Now you can put this into a sine function, all these, and then you will get something like this. Now, why do we do this? There might be some data in our hand which looks like a sine function, and we try to fit this as sine function. So what we basically do is we shift it vertically with D, and then shift it horizontally with C, so that it gets close to the data we have, and stretch also vertically by this figure, and stretch or compress by figure. Here is a compress. If you remove pi over v, we show period sine function, because when x is equal to c, this thing is 0, so you start the sine function. When x minus c is equal to b, you get 2 pi. So the period you also arrange the period vertically and horizontally shift, and you get a general sine function like this. In this way, you can fit some given data to the sine function. And in fact, your book has an example on this. In this example, the weather in Alaska is fitted to a sine function. It's a function of its time, and time is shown in days. You can see in your book that preparing a general function and trying to fit data, we use properties, vertical shifting, horizontal shifting, and vertical shifting, horizontal shifting, etc. And that shows here the figure now. Here D is the vertical, that's x-axis, that's y-axis. So we shift it upwards with some positive number, and then the amplitude, it's called the amplitude, that's vertical scaling. And if A is greater than 1, it reaches vertically. If less than 1, it compresses vertically. And B is, of course, a period. You start from here, and then the period is gone finished here. That was just an example about modeling certain phenomena or certain data with a sine function by using the properties function like vertical scaling, horizontal scaling, vertical and horizontal shifts. Okay, this about finishes our review of your high school knowledge, and we will now move on to chapter 2. Now, tomorrow I will give you your first homework, which is about chapter 1, and you will have enough time to solve the homework. I will send you an email and the homework is ready tomorrow. And so you can go there and try to solve the problems. Any questions about chapter 1? Okay, let's now move on to chapter 2, which is limits and continuity. We start this chapter with rates of change of functions and tangent lines. What are the relation between the rates of change functions and tangent lines to the curve? These curves are of course f of functions. Let's now assume that there's a function f of t which measures the distance traveled at time t, distance traveled by an object at time t. Now, if you want to find the average speed of this object between t1 and t2, then you calculate the distance traveled between t1 and t2, and you divide this by 2 minus t1. So that will give you the average speed of the object. Let's now see a table about that. Now our function here is 16t squared, which measures the distance. Okay, there are some questions. Let me answer them. This will be a homework which will be in MyLab and Mastering. This is the internet platform led by Pearson. And as I told you before, this platform is not integrated to be locked. So you can go to course contents in the Blackboard. Here there's a connection to MyLab and Mastering. You will see that, and when you click it, if you're registered to the platform, you will immediately go to my course and you will do homework there. So the homework is about chapter 1, which is actually the review of your high school knowledge. It's to refresh your knowledge on mathematics by solving these problems. Okay, let's go back to lecture. Now, here our function is 16t squared, and t1 is, let's say, t0, and t2 is t0 plus h, where h is now a positive number. So here, t2 minus t1 is basically h. Now, y2 minus y1, or f of t2 minus f of t1 is t2 t0 plus h. So we take the square of this, and t1 is 16t0. Okay, so this gives us the average speed of this object, which moves with f of t, which is 16t squared. Now, we have two starting times now. t0 and t0 is equal to 1 and t0 is equal to 2. So when I put h is equal to 1, t0 plus h is 4 times 64, and minus 16, which is 48. Now when t0 is 2, that's 9 times 16, because 2 plus 1 is 3. 9 times 16 minus 64, which is actually 80. So the average speed of this object between these two times, if you start measuring from t0 is equal to 1, that's 48. If you start from measuring t0 plus 2, t0 is equal to 2, that's 80. Okay, here the difference is the object accelerates more, so when you measure from t0 to t0 plus h, you have higher speed, higher average speed. Now let's reduce h one by one. Let's put h01. Now if you calculate this, you'll get 33.6, which is a big difference because we reduce h 10 times. If and here that's 65 over 6. And yet to reduce it more, we are trying to move close to 0. Okay, 100 times, that's 32 plus 0.16 here, and 64 plus 16. Now, if you reduce it 1,000 times or 10,000 times, it seems that this goes to a constant number. So 0 and equal to 1, and constant number at t sub 0 equal to 2. So what's happening here as h goes towards 0, and we can continue here, reduce it 100,000 times, etc. And we will still have 32 something here, 32 something here, and here 64 something. Okay, let's try to figure out what does this give us. Now that same is true for average rate of change of a function y is equal to f of x. If you have a function like this, the change in y, we call it delta y, and the change in delta x, that gives you average rate of change of this function if you move from x1 to x2. Within this interval changes. So delta y over delta x gives you the average rate of change. Here, of course, h is not equal to 0 because h is equal to 0. This is 0 divided by 0, which is not a real number. So we won't get h to 0, but we can get very close to 0. As long as this is not 0, there's no problem. Okay, now let's look at it geometrically, what's happening. Here we have a function f of x, that's x1, so you have a point P in fx1 and x1. Okay, fx1 is the y coordinate, this is y1, and here x2 and y2. Now, you take the ratio of delta y alpha x, okay, divided by delta x. Now, any 2 points, if you join them by a line on a curve, this is called a secant line. Now, the ratio actually gives you what? The slope of the secant line. The ratio, that's what the ratio gives you. Because this is a right triangle here, delta y over delta x is tangent of the angle here between the secant line and the horizontal. So, rate of change of a function between 2 points gives you the slope of the secant line. That's geometrically, that's what we see. Now let's continue from here. Now the tangent line is something different. It's not a secant line. It just touches the curve at one point. Here, if you have a circle, the tangent line to the circle is perpendicular to the radius and it touches the curve at point. Now let's see this figure now. You have point P and point Q here, and this is joins point P and Q. That's the secant line. Now, what happens if I move Q towards P? Okay, the slope of the secant line changes, and at this point, it gives the tangent line. You can, here we approach P from this side, okay? And here we approach P from this side. That secant line here joining Q and P. Now I move towards P, and then at the end I will get a tangent. Okay, so now the average rate of change. Okay, so let's look at this figure. We have a function y is equal to x squared. Now p is at 0.24, and here we have 0.2 plus h x coordinate, and y coordinate is 2 plus h squared. So that's the difference, delta y plus h squared minus 4 over h is the secant slope, which is equal to h plus 4. Okay? Because if you calculate this 4 plus 4h, 4 plus 4h plus h squared, so 4's cancel out, h cancel out, 4, you end up with h plus 4. Now what happens if I h slowly to 0? Now, this is the secant line. Now you are moving this point towards P, and you go like this, and at the end you have the tangent line here. H is 0, tangent line is a value 4. Okay, what does this represent? The secant line here represents the average rate of change of the function between these points. The tangent line touches the curve at one point. That's the instantaneous rate of change of this function. When you talk in terms of velocity, like in the previous example, well, secant line, the slope of the secant line gives the average velocity, but the tangent gives the instantaneous velocity. So this is the basic difference. Okay. Let's continue. Here's another one. That's that plot curve shows the growth of fruit fly population in a controlled experiment. Okay, again you have 2 points here, P and Q. Okay, P has coordinates 23, 150. Here the axis is T, and that axis is number of flies, fruit flies. So 23 and 150, that's 45, 350. Okay, so the average increase of the fruit fly population is 8.6 flies a day. And that's this difference, delta P, 190 divided by 222. So that's average rate of change of the fruit fly population between these 2 points, of course. Now, if you continue, now if I move from here towards here, then 8 plus 6 and 10 plus 8, as you can see, T is reduced and the population is reduced. Of course, 340, 330, 310, 265, and the time T changes from 40 to. And now slowly, it's again coming to a constant number, which will give us the tangent line at this point if we move on like this. Okay, so this was sort of an introduction to limits. As we get close to something, as we have seen, the second lines, as we get close, point turn out to be tangent lines, relation. And we've seen this geometrically with secant lines and tangent lines, and secant lines gives the average rate of change of a function between 2 points, where the tangent line gives us the instantaneous rate of change of a function at a given point. Let's now define what we say, let's make a definition of the limit. So we have a function f of x over an open interval, x of 0 minus h, x of 0 plus h. The symmetric interval around x of 0. This function is defined in this open interval. It may not be defined at x of 0. I don't care about this. It may be defined, it may not be defined at x of 0. If f of x approaches arbitrarily close to a real number L, it's arbitrarily close. That's not a very mathematical definition. That's a crude definition of what we mean by limit. For all x sufficiently close to x of 0, not at x of 0, sufficiently close to 0, we say that f of x approach to a limit L as x approaches to x 0. Okay, so then we write it like this. Limit as x goes to x of 0 of f of x is L. We write this. Now, approaches arbitrarily close or sufficiently close, these are not really mathematical concepts. These are crude concepts. We will give more precise definition of the limit later on. But the basic idea here is that when x moves toward x of 0, either from the right or from the left. From the right, I mean that value greater than x of 0. From the left, value is less than x of 0. So as our independent variable gets close to some point, x of 0, how does my function behave? What's the behavior of function? Does it approach to a real number or not? That's what limit is about. I don't care what happens x of 0. and the function may not be defined as of 0. But what I'm interested in is that how does my function behave when my independent variable approaches to a point. So this is the basic idea about the limits. Let's look at this function. Okay, y is equal to f of x, which is given as x squared minus 1 divided by x minus 1. Now, at x equal to 1, this function is not defined because that's 0 over 0. When you put x is equal to 1, x squared minus 1 is 0, and x minus 1 is 0. So the function is not defined at x equal to 1. So now, but when x is not equal to 1, I can cancel out because I can factorize x squared minus 1 as x minus 1 x plus 1, and I get y is equal to x plus 1. That's a line, right? That's a line. And here in this line, as you approach x equal to 1, the function approaches 2. So the limit for this function is 2. Okay, how about this function? Okay, this function is not defined at x equal 1, however, it's defined everywhere else. So what's the limit of this function? Now, as you can see, as you approach 1 from this side like this, you approach 2. As you approach from this side, again you approach 2. So the limit must be 2. However, the function is not defined, but I don't care about this. My function behaves like the limit, like there is a limit, because it gets arbitrarily close to 2. So this function has a limit 2, this function has a limit 2 also as x goes to 0. But I don't put x is equal to 1 here. I can get arbitrarily close to 1. So that will be a very small number, but that will be a very small number too. So the ratio of these small numbers will be equal to 2. Okay, so now let's look at this table. This table shows us very clearly what happens. Now x, I'm going to calculate f of x, x squared minus 1 over x minus 1, when x is not equal to 1. I approach from the left first. 0.9 is cost to 1. And if I calculate, that's 1.9. Now I will approach from right here, values greater than 1. When I calculate, I find 2.1. Now I approach more to 1. That's I put x 0.99. And I obtain f of x is 1.99. That's closer to 2. Now I approach more from the right hand side, from values greater than 1. Now x is 1.01. Now that's 2.01, the value of function. So on both sides, I'm getting closer and closer. So I get more closer, 0.999. That's what I get. 1.001, that's what I get. Now I put 6 nines here. 1.6 nines here, very close to 2. And I put 1.000001. And I get 2.001. Both these numbers are close to 2. So I know that this function has a limit 2. That's not a very rigorous proof for that limit is equal to 2 to make it more rigorous. But I don't care what happens at x equal to 1. Because when x equal to 1, I cannot cancel out x minus 1 factors. If x is not equal to 1, I can cancel out common factors and calculate these numbers. That's how I calculate numbers too. Let's continue. Okay, let's look at these three functions. One is this, which is not defined at x equal to 1, but it has a limit too, as x approaches 1. Now this is x squared minus x minus 1 when x is not equal to 1. When x is equal to 1, I put value as 1. Okay, so that's the function value at 1. But still, this has a limit too, because when I approach from here or here, my limit is 2. I don't care the definition of the function at 1 or anything else. But this has limit 2. Now this function, of course, there is no problem here. I can just substitute 1, that was why h of x is equal to x plus 1, and that's the limit I can find the limit. Okay, so these three functions have the same limit, although they are different functions. This one is not defined here. This one is defined at 1, but at some point out of this line. And this is, of course, the line. So all three have the same limit. So, in order to summarize, we don't care about what happens to the function x of 0 when you approach x of 0. We care about how my function behaves when I approach x of 0. Does it go to a limit? That's the basic idea about limits. Now you have y is equal to f of x. Y is equal to x is some function. I mean, there's no problem finding the limit of this function. If you are going to calculate the limit as x goes to c, it's equal to substitute. Here, that's the same thing. That's a constant function. Y is equal to k all time. So the limit is for all x, the limit is k. The limit function, because it's a constant function, have the same limit as at all x. Okay, so we talked about functions who have limits as they approach to some, as the independent variable approach to some value. But there are some functions which do not have limits as the independent variable approaches to some point. Let's look at this function. Y is, that's a piecewise defined function. Y is 0 if x is negative. Y is equal to 1, x is greater than or equal to 0. So it's defined everywhere. This function is defined for all real numbers. Now let's look at the limits. If I approach 0 from the right-hand side, as you can see, I get arbitrarily close to 1. So the limit is 1. But as I approach 0 from the left-hand side, the limit is 0. So this function does not have a limit because there is a jump at x of 0. Okay? There is a jump at x of 0. When you approach from right, you get one value. When you approach from left, you get another value. Now, basic definition of the limit, as you approach from both sides, the numbers are the same. So this is called the unit step function, and this does not have a limit at x equal to 0. Now let's look at this function, 1 over x. When x is not equal to 0, 0 when x is equal to 0. So that's the value of the function x of 0. This function does not have a limit because when you approach to 0, this function grows immediately, grows too much. You cannot put a number. Give me any number, 1 million. I can find values of x greater than 1 million. So that cannot be a limit. So this function grows too much, or on this side, if you approach 0 from the left-hand side, it gets very small too much, big negative numbers. So there is no limit at x equal to 0 to this function. Now let's look at this function. Y is equal to 0 for x less or equal to 0, but y is equal to sine 1 over x for x greater than 0. Okay, when you approach from the left, you have a limit, but when you approach from the right, you don't have a limit, because when x is close to 0, 1 over x is a very big number, and the function oscillates wildly close to 0. You cannot put a value here or here to take the limit. It's not possible. It's very small changes of x, sine 1 over x oscillates too much, and you cannot keep it at one place. So this function does not have a limit because the function oscillates too much at x equals to x of 0 when you approach to this number. Okay, let's look at limit laws. This is sort of obvious. Suppose you have two functions, f of x and g of x, and the limit as x approaches to c of f of x is L, and the limit g of x as x approaches c is M. So the sum rule is straightforward. Actually, we are going to prove this when you have a precise issue of the limit. Now, if you sum the two functions, the limit as x goes to c is L plus M. Or if you take the difference, that's L minus. If you multiply by a function, by a constant, sorry, a times the limit a times L, multiplication of these two functions will be L times M. The ratio will be L over M. The limit of the ratio will be L over M. Here M must not be 0. Now the power rule, f of x as x approaches to c is L to the n. Now L must be a positive integer here. By taking the root of a function, the limit of the root of a function will be root of the limit, but this should exist. Okay? And if L is negative, if n is 2, there is no, square root of a negative number is not fine. So you have to be careful about by taking the limits of functions with roots. Okay, these are the sum of the rules for limits. These are sort of obvious to come from the definition of the limit. Okay, limits of polynomials. It's easy because there is no problem here. These are functions defined for all real numbers. The limit as x goes to c of p of x is p of c. Just substitute c instead of x here, and that's what you get. Now, the limits of rational function can also be found by substitution if there's no problem in the denominator. Here, for instance, this example, x squared plus 1. There's no problem in the denominator. This is never 0. So, here we have a real number divided by a non-zero real number, so the result will be a non-zero number. So you can just substitute the c instead of x here to find the limits. Okay, so there is no problem here. But here we have a problem because x squared minus x, when x is 0 or x is equal to 1, there's a problem here. Okay? Because the denominator is 0. So the first thing that you can do is factor both the numerator and the denominator. Now if you factorize this, you'll get x plus 2 and x minus 1 multiplied by x minus n. Here you have x minus 1. Now these cancel out if x is not equal to 1. So you have this. Now as x approaches 1, you can find the limit here. So that's 3. 1 here, that's 3 here, 2 over 1 is 3. Okay, so you can try to cancel out the 0 denominators. Okay, that's right. Now, we have x squared plus 100, x square root minus 10 divided by x squared, and you are looking at limit as x approaches to 0. Okay, so when x approaches to 0, you have 10s cancel out in the numerator, and the denominator is 0, so you have 0 divided by 0, which is not a real number. So what you can do is you can multiply both the numerator and denominator by conjugate of this expression. Conjugate is you put here. So when you multiply, you get x squared plus 100 minus 100. So it will help you to cancel out some of the factors. Okay, so but this is multiplying by 1. Okay, multiplying by a constant by 1 doesn't change the limit. So you do this multiplication, then you get this, and you calculate the limit. So you just multiply by 1 to eliminate some of this. Basically, you eliminate x squared here, which is important. Okay, that poses the problem. Okay, let's now give a break for...
Teacher,
Yes.
what happened in here x square?
Sorry? Sen.
Şurada x kare nereye gitti hocam?
X kare şöyle gitti. 100'ü götürüyor.
Yok, alt kısımda yok oldu da. Ya sıfırla.
X sıfıra giderken limite burada. Şimdi 100 eksi 100 sıfır. Burada x kare kaldı sadece. Aşağıda da şurada x kare var.
Evet.
Bunlar gitti. Aşağıda x kare artı 100 artı 10 var.
Teşekkür ederim.
X kare gittiği için 1. Burada bu var. Şimdi burada eksi sıfıra 0 koyarsam burası 10, burası da 10, 20. 1 bölü 20 limit oluyor.
Tamam.
Break for 8 minutes. We will start at 11.